So let's model the atmosphere in here now. Yeah, we're going to need to go back to Photoshop a sec. Let's consider the effect of an atmosphere. For one thing, this is going to be a real simplification, but also this is like the real fundamentals in a subject that you don't necessarily deal with all the time. So what I'm going to do is I'm back in Photoshop here. Let's put an atmosphere in. Let's put the planet in underneath. It's going to be dark blue for some reason. What is affecting the temperature here? So what we've already done, we had energy from the sun coming in, and that was our insolation. And then we had energy leaving from the surface of the Earth, and that was this term. So that's what we had previously. So when you introduce the atmosphere, you introduce a problem with one of these radiative forcings. And the thing that we had to remember about radiation now is that it's not all one frequency. So the energy that comes in from the sun is generally higher frequencies. So it's going to be more ultraviolet, it's going to be more visible. The reason for that is that the sun is very hot. And in general, the hotter an object is, the higher its temperature, the higher the frequency, or equivalently, the lower the wavelength of the radiation that it gives out. So by that logic, the Earth is very cool by comparison, so it gives off longer wavelengths or lower frequencies. And that's important because different substances absorb different wavelengths of light in different ways. To be specific, the atmosphere doesn't absorb the short wavelengths that come in from the sun. They go straight through. And obviously I'm simplifying here because there is in the atmosphere that does absorb short wavelengths, like ozone, for example, is very good at absorbing certain kinds of ultraviolet light. But oxygen and nitrogen, because they're diatomic molecules, they don't get excited in that frequency band. They do get excited, and so they're very good at absorbing the longer wavelengths, the smaller frequency radiation that the Earth gives off. So in actuality, this arrow of radiation doesn't go through the atmosphere. It gets absorbed. We now need to introduce a bit of extra terminology. Let's have temperature of ground, Tg, and temperature of atmosphere, Ta. The incoming solar radiation passes straight through. We don't need to change that. The ground will radiate, as we said before, which is sigma Tg to the 4th power, and that gets absorbed by the atmosphere, except it doesn't entirely get absorbed by the atmosphere. What will happen is some of it will escape. We write that as the transmittivity of the layer. What I'm going to do is write that as 1 minus a, lowercase a. That is the absorption coefficient of the atmosphere, and the logic there is that the transmission plus the absorption equals the total amount of energy. We're not assuming any reflection that's going on. 1 minus the absorptivity is the fraction of that radiation that actually escapes to space. However, the atmosphere, because it is a radiative body, it is a thermodynamic object that has a temperature, it also radiates at its temperature, Ta to the 4, but it does so at its emissivity value, which Kirchhoff's law in thermodynamics states is equal to its absorptivity. So that's why I wrote this as 1 minus a, so that we only have one variable to keep track of. But the thing to remember is the atmosphere isn't blocked from emitting downwards as well. The Earth obviously can't emit going downwards into the rock because there's nowhere for the radiation to go, but the atmosphere can. So it actually radiates effectively twice. The amount of energy that it gives off is twice the absorptivity, which equals the emissivity, times sigma times the temperature of the atmosphere to the 4th power. And so that energy that's given off by the atmosphere is absorbed by the ground. This is the energy exchange that's going on, basically. So if we wanted to write this in code, what do we need to modify of what we had before? Let's look at the ground. That's the first thing that we've already written. So what do we need to change? The amount of energy that's coming in is the same. That doesn't get changed. The amount of energy that is leaving is also the same. But we now have this extra term. We have this absorption that's been given off by the atmosphere. I'm going to make an assumption here, which is that the surface area of the atmosphere is the same as the surface area of the Earth. Obviously, that's not exactly true because the atmosphere is the outside of a sphere of a slightly larger radius than the Earth, but functionally, the atmosphere stops at the order of tens of kilometers. So when you're comparing that to 6,400 kilometers, it's a really small difference. So I'm going to make an assumption there. Just wanted to point that out. What we now need to do is add in an extra source here of energy, which is that atmospheric emission, which is the absorptivity. And I'm going to set that to be 0.25 multiplied by sigma, multiplied by temp atmosp. So that's sphere because we're radiating over the whole thing. So that's the extra term here. Now, what we can effectively do, actually, is not change the temperature of the atmosphere and assume that the atmosphere just stays at 250 Kelvin. It just doesn't change. Let's try this. So what we have here is the atmosphere is constant at 250 Kelvin. That's currently not changing, it's just static. But it is, because of this extra term here, having an impact on the planet's temperature. So now, before the planet was being at equilibrium at about 273, it was about 0 Celsius, or 273 Kelvin. Now it's actually at about 290. So the atmosphere being at 250 degrees Kelvin, that extra source of energy for the ground, is enough to raise the temperature. Now, that's actually kind of interesting because I picked 250 completely randomly. So at about minus 20, this big chunk of atmosphere is producing approximately the right result. It's producing approximately the correct global average temperature. Just because the atmosphere starts at 250, the temperature of the atmosphere is going to affect it, right? So it's going to be T to the 4. So if we change that to be 200 as well, then the planet's going to equilibrate at a slightly lower temperature. It's probably going to be like 280 maybe. But there we go. You get the idea. Okay, but now this is where sort of coding kind of gets magical for me, in that you can start doing these really nonlinear systems that you could not predict how they are going to change as time goes on. So let's also now vary the temperature of the atmosphere. We now actually need to change the heat capacity here. So we need to have heat capacity Earth and heat capacity Atmos. And let's make that 1E3. So it's going to be 100 times smaller. It's basically 100 times easier to change the temperature of the atmosphere than it is to change the temperature of like rock, which is an approximation, but not terrible. Right, so what's the energy exchange that's going on here? So the source of energy for the atmosphere is the absorptivity, it's epsilon in our code, multiplied by the amount of energy given off by the Earth. It's going to be sphere times epsilon times sigma temperature planet, sorry, not ground. It's the 4. And then it's minus 2 times sphere times epsilon times sigma temperature atmosp, because we've got one contribution heading this way and another contribution heading this way. So it's 2 times epsilon, which we've written here as a for some reason, multiplied by sigma times TA to the 4, which is what we've got here. Yes. So that's interesting. The temperature of the atmosphere immediately sunk. Let's make this a wee bit bigger. And now they're both trending upwards. And so the planet is equilibrating at... that might end up at closer to 290. For those of you who don't know what I'm doing, there's the numbers that appear down here. And the atmosphere is equilibrating a little bit cooler than it did before at about 240. But this is where we can do something fun. So this epsilon value, which is how effective the atmosphere is at intercepting radiation, that's just numerically prescribed. Let's say that we then make the atmosphere super, super good at absorbing radiation. It's suddenly incredibly dense or full of clouds or something. What would happen then? So I think before the planet was at about 290 and the atmosphere was about 245. So what we have here then is, as I said, we made the atmosphere much better at absorbing the radiation that's coming up from underneath. And so the planet is now 40 degrees Celsius on average. And the atmosphere is about minus 10 Celsius. So as you'd expect, when you have not even a denser, because we haven't changed the heat capacity, we've just had an atmosphere that's chock full of some molecule that is really good at absorbing long wavelengths of radiation. And that heats up the planet. What we just simulated is is effectively a greenhouse effect, like a rapid change to a greenhouse effect. So that is planet-wide thermodynamics. We've shown that we can numerically simulate changing the temperature of a planet and its atmosphere in tandem. One thing before we move on, actually, is that, as I said, we're approximating the whole atmosphere to just be a slab. So when we actually go back to doing this a bit more realistically, you'll see that the atmosphere is at -20, so like 250 Kelvin or whatever. And you might think that's too cold. But remember, that's the average temperature across the whole atmospheric column, weighted by density. So realistically, you're looking for what the temperature is, maybe 5 kilometers up over the surface, maybe. The temperature is going to be lower than you would experience at the surface, is what I'm trying to get at. This is one of the reasons why this is a bad model of the whole planet, because obviously there are different layers in the atmosphere. There's literally subdivisions in the atmosphere that I've studied, but within those subdivisions there's a continuous decrease in density and a variable temperature, varying rates of the emissivity, the epsilon value. And so this is why this is only a toy model. This isn't what climate scientists would actually use, but it's a nice kind of demonstration.